Alright guys, so this is the solution to the bell ringer here in class. We have a diver up here who is jumping off of the diver up here, jumping off into the kind of substance below. It's watery-ish. It's not necessarily water. Who cares? And they dive off a 55-meter cliff, so they are not in the substance for 55 meters. And then once they hit the substance, it takes them 8 seconds to stop. So we're going to look at this problem for the impulse momentum theorem. I know it's the impulse momentum theorem because if I look at the individual person, I do force diagrams on the person. There are net external forces in both cases. For example, when the person jumps off, the force diagram is just force of gravity, and that's it. They're in free fall. And when they hit the water, they still have force of gravity, but the substance is going to push them upward. And I know it's going to push them upward greater, we'll call that substance, because the person is going to slow to a stop. They're going to accelerate. They should be following Newton's second law. So this tells me I should use the impulse momentum theorem. That being said, while I say the impulse momentum theorem, as you look up here and you just see force of gravity, that should trigger a, hey, I know what that acceleration is. I don't need to work hard. I know the acceleration is g, so I'm just going to go ahead and use kinematics because I actually have 3 kinematic variables here. I know that the velocity initial is 0. They're jumping off of a cliff here. Right? The acceleration, we're assuming this is on Earth, is negative g because I'm establishing that up is positive here. That's important. And I know that the displacement is negative 55. It's been a minute since we've done some kinematics, so don't forget to say negative. Now, if you want to call that y, that's completely fine. It's not going to change much of anything. Just, I suppose, makes it a little bit easier potentially on you. So, kinematics, those are the 3. I'm looking for this one right here. So I'm using this equation. Pi y squared plus 2a delta y. That will cancel. Square root both sides. And we get that the velocity final is going to be the square root of 2a delta y. So I plug in 2 times negative g times negative 55 meters, square root the whole thing, and I end up with 32.8 meters per second. But keep in mind, I gotta go, wait a minute, it's going down. I've established up as positive. This should end up as a negative, and it does because this causes a plus or minus, so I'm gonna choose the correct one in a minus. So this right here should be the speed when the diver boom hits the water. That would tell us our initial velocity of the water. Okay, now I'm going to erase this next part so that I have enough space for it. I'll leave the left side, of course, here, so if you need to take in a moment, great. But let's move on to the next side of things, and we'll just carry this particular answer over. So let's go and move you just up there, okay, and reestablish that is the velocity final y, or velocity, I should say velocity final of when it's in the air. Now we're going to hit the water, so here's where we use the impulse momentum theorem. Keeping in mind, once again, the impulse momentum theorem is essentially just Newton's second law, and so quite frankly you probably could use Newton's second law here as well, but since we're in the momentum chapter, we should be practicing with momentum. Okay, and the main reason I'm doing this problem right now, because you've done a decent amount of impulse momentum theorems, is to focus on this. We've primarily done problems where the net force is given. Like there's been a football player, right, running, and we've told you, for example, that the force, just the net force on it, is that. What we have not yet done is dealt very much with what if there's 2 forces, like here and here. Now, this is relatively easy, but I just wanted to make sure to show it to you. The net force here is, you see, everything's in the y. So, whenever we sum the forces in the y equals mass times acceleration, and then right over here we would say the sum net force in the y is force of substance minus force gravity, just because that's up, and this one's up, and this one's down. That is the net force. We don't need this piece over here. We don't need that piece. And so that just goes right there. So that's going to be force of substance minus force of gravity. Okay. times time equals, let's decide what we want for change in momentum. I could say PF minus PI. I think probably our best bet, since we're dealing with velocities here, is mvf minus mvi. What are we looking for? We're trying to figure, I don't know if I told you that. Oh, my apologies. Very beginning, we were supposed to be looking for what is the force of the unknown substance. That's on your powering, so you hopefully would have known that ahead of time. But so here, let's cancel what cancels. Keep in mind that this is velocity final y. It's final for the section where they were diving, but of course now we're going underneath the water. Okay, and the question is, how much force is required to get it to stop in 8 seconds? So that means that while it was final before, now it's initial. So this is the VI, I should say, is our negative 32.8, and VF, it's going to stop, so that should be 0. Then I do algebra. Keeping in mind, I cannot move this first because t should technically be distributed. So the first thing I should do is divide that t out. So I should get negative vi over delta t. And then that would leave us with fs minus fg. And a simple add fg to both sides, or add mg to both sides, is the solution. So I plug my numbers in here. I get negative 55 kilograms. That negative, of course, came from the negative right there, okay? And times the negative 32.8 meters per second. That negative, of course, came from the fact that it was downward. So yes, absolutely, they will cancel, which should make sense. Divided by 8 seconds plus 55 kilograms times g. And our final answer, we plug it all in, is 764.5 newtons. Okay, a couple of quick things to go over. Big mistakes that are typically made are as follows. Okay, one, the sign. The sign, we forget to put that negative from the kinematics. Technically, you could have said at the very beginning and said down was positive, which would have made that positive 32, but technically then our answer over here, our final answer, should be negative, because this substance does push upwards here. So whatever we establish is upwards, either positive or negative, that should be our corresponding answer. And of course that would happen because this would not be negative. This would not be negative. And this guy actually, where is it at? Force of, and then this right here would flip. Force of that would be negative, and force of gravity would in fact be positive at the beginning, which would cause the changes we saw. Other big mistakes that are regularly made is this 8 seconds is really darn tempting to put in your kinematic variables. It doesn't go in your kinematic variables because obviously the kinematic variables for when we were falling, and this specifically said that it was the 8 seconds while it was stopping. So answer is 764.5 if up is positive, and negative if up is negative.